we are continuing module 2. In this module, we are discussing different nonlinear effects, and so far we have discussed second order process, third order process, and in the third order process we have seen two self-affecting processes. The first one is self-focusing and the second one self-phase modulation. When all three input beams are identical in this equation, and if they propagate along the same direction, then these three input beams can be collectively considered to be a single input beam. So I have this medium which expressed by this third order nonlinear polarization, and I have, we can consider as a single beam propagating along this direction. In the end, effectively this input beam is expressed as, which is nothing but E1, which is expressed as AT envelope function e to the power I omega 1t minus k1z. So that's the very familiar expression for an ultrafast pulse, which is having an envelope function and the carrier wave component with center frequency omega 1. So this nonlinear polarization expression suggests that the beam, we get back the beam E1, but it is affected by its own intensity A1. When pulse's own intensity forces its spontaneous focusing, it is called self-focusing. We all know that a lens is a transmissive optical device that forces a light beam to focus. So this is a lens and it focuses the beam. At the focal point. So this is called focal length. Similar to the lens, a medium having third order nonlinear polarization, a rectangular nonlinear medium can also behave like a lens and can focus a light beam. This occurs through the nonlinear contribution to the refractive index. Generally, every medium has its own refractive index, that is N naught, but the nonlinear expression for refractive index is this, which depends on the intensity. N naught plus N2 multiplied by its own intensity I. So it's intensity dependent refractive index, which means that if I take a beam, we haven't discussed this beam, the transverse electromagnetic mode of the beam. When the beam is propagating along this direction, and if I place one piece of paper, then we see a circular spot, and that circular spot is called transverse electromagnetic mode. And if we take a cross section of that spot, then what we get? A Gaussian distribution of the intensity. This is not the Gaussian pulse in time domain. This is the Gaussian distribution of the intensity, is a spatial distribution. So this is your x naught with respect to, so this is the axis. With respect to this axis, we see that in the middle of the beam, so this is the cross section. If the beam is propagating along this way, and then if I place one piece of paper, then I get this cross section, and the middle of the beam intensity would be maximum. This is the maximum intensity, and that's why, and we have taken a cross section like this, and we are representing this one. This is my x-axis, let's say. So middle of the beam is maximum, which suggests that I will have this nonlinear refractive index maximum here, maximum refractive index, and the wings will have lower refractive index. This intensity dependent refractive index is called optical Kerr effect. This is a direct consequence of nonlinear contribution to the refractive index, which depends on intensity. Here N2 is the nonlinear refractive index, which is expressed by chi3 third order susceptibility divided by 2 n naught. N naught is the linear refractive index. This is linear refractive index, and N2 is nonlinear So because of this nonlinear contribution to the refractive index, we get self-focusing of the beam. How does it happen? It is shown here in this figure. Let's say the beam is trying to come from lower refractive index regime to the higher refractive index regime, and it will definitely bend, and due to this bending it will start focusing the beam. And we know that this regime would be higher refractive index because the intensity is high here, and this regime would be lower refractive index because intensity is low here because of this Gaussian distribution of the intensity of a Gaussian beam. So for a Gaussian laser beam, the spatial intensity profile results in spatial variation of refractive index, which is higher in the center than at the wings. This variation in refractive index acts as a lens, self-focusing lens, and the beam converges and eventually gets tightly focused. So this is called self-focusing. On the other hand, the intensity of the pulse also affects its phase, and that's why it is called self-phase modulation. Intensity dependent refractive index imposes an additional phase shift to the pulse envelope during the propagation. We'll find out how this kind of additional phase can be introduced to the pulse very soon. To visualize the effect of the self-phase modulation, we will first express the electric field of an incident pulse propagating in z direction as EZT equals AZT e to the power I omega naught t minus kz. This is again the very familiar expression for a pulse. This is envelope function, this is carrier wave part with center frequency omega naught along propagating along kz direction, which is z direction here. We assume that we have a nonlinear medium, that is self-phase modulation medium with thickness L, and we have to express K in terms of its nonlinear refractive index. So at z equals 0, when the pulse is just entering the medium, I can express electric field as this, where z equals 0, that is why kz term is gone from this equation, and at z equals L distance I can write down omega naught t minus 2 pi by lambda naught n nonlinear multiplied by L. This k has been replaced by this nonlinear refractive index. So, if we express like this way, then we know that nonlinear refractive index is nothing but n naught plus n2 of I, intensity dependent refractive index, and that is exactly what we have inserted here. Then little bit of rearrangement, we get the final expression for the electric field. This electric field is E field of self phase modulated pulse due to propagation of L distance in the medium. Once we get the electric field, then we can write down that this expression as this, where E 0 t is the field without the medium. If we did not have the medium, then the pulse would have propagated L distance, and due to the propagation the field should have been like this. But because the medium is present here, we have introduced additional phase, complex phase in the medium. This mathematical expression for self phase modulated pulse after propagating L distance in third order nonlinear medium suggests that the time dependence of the additional temporal phase, more specifically the complex temporal phase, complex because it is in the complex notation, due to self phase modulation comes from the time dependent intensity, this part. The induced phase changes the behavior of the pulse. Now, we can remind ourselves, in module 2 we have seen quadratic temporal phase. So, a transform limited pulse was expressed as E t equals A t e to the power I omega naught t in time domain, and we said that if it is a sharp pulse due to second order nonlinear temporal phase, then we can write down E t equals A t e to the power I omega naught t plus phi t, the additional temporal phase. This is called temporal phase, and we have taken example of Bt square at some point in module 2, and we have seen that that represents quadratic temporal phase, which gives chirp in the pulse. Similarly, here total phase, if we look at the total phase phi t, total phase which is obtained for the self phase modulated pulse, we get omega naught t minus k naught L minus this expression, which means I have now additional phase, temporal phase, which is also called complex temporal phase. And whenever we introduce complex temporal phase to a pulse, we have chirp. In this case, CHARP is very complicated, and the way we realize CHARP by considering instantaneous omega. Instantaneous omega, if it is varying with respect to time, in module 2 we have studied, then it is CHARP. So if we get the instantaneous omega, which is nothing but the first derivative with respect to t, we get omega naught minus this expression, and this has time dependent part, IT. Time dependent part in the temporal phase is coming due to the intensity of the pulse itself. This suggests that if I have cell phase modulation in the medium, then definitely I am going to introduce CHARP into the input beam. And CHARP is not as simple as BT square. It is extremely complicated CHARP depending on the intensity. This di dt term. And whenever we are introducing CHARP, we know that the pulse is going to elongate in time. Now we will look at the frequency domain expression. We have already seen the time domain expression, and we know how to convert to frequency domain. The corresponding spectrum of the output pulse, which is self phase modulated pulse, is expressed as square modulus of the Fourier transform of the time domain field, and this is the spectrum. We can assume a Gaussian intensity profile for this IT, and in that case we can write down with the first order approximation. This is a very simple approximation we are making to get an analytical solution. Otherwise we have to use numerical solution, but to get analytical solution we have this IT expressed in exponential series up to first order, and if we do that, then with the help of little bit of math one can show that the spectrum expression for the spectrum of the self phase modulated spectrum looks like this, and the term given here suggests that it will always spread as a function of L, which is shown in this figure. So this is the thickness of the crystal, L distance. I started with a transform limited pulse, a Gaussian nice looking spectrum we had. As it is propagating along Z direction, L direction, we are seeing that new frequency components are created and the pulse is broadening. So this equation clearly shows that the spectrum will broaden as a function of the crystal thickness L, which is depicted in this figure. New frequency components are generated due to self phase modulation. Extra frequency components broaden the spectrum on both sides of the center wavelength. So here the center wavelength was at this point, and it's broadening on the both sides of the center wavelength. The broad spectrum generated in this manner is called continuum generation or white light generation. If an ultrafast pulse centered at 800 nanometer is focused into transparent nonlinear material which can potentially exhibit self phase modulation, the emitted pulse will appear as a pulse of white light, and it will be broad as well. Broadening is appearing because of the introduced temporal phase. Most common medium which is used for white light generation is sapphire crystal. So thus far, all the examples of second order, third order processes which we have discussed thus far suggest that nonlinear effects are very interesting and can be very useful pathway to achieve frequency conversion. In nonlinear frequency conversion process, however, we have to remember that one limiting factor is phase matching.